Okay, thank you, everyone. I'm Marco Mambelli from Fermilab, and I will be talking about using Apptainer in a pilot-based distributed workload system. So the system that's used in many HCC collaboration is sorry. Okay, back. It's a GlideinWMS. This is a pilot-based resource provisioning tool that is used by many experiments. It provides reliable and uniform virtual clusters using jobs that are submitted to heterogeneous resources. We use underneath HC Condor, which is a batch system, both for the cluster that we provide and for some of the mechanisms that we use to access the different resources. So first, we are in a high-throughput computing environment. That means that we split the scientific computation in many independent parts, small parts, and we resolve them on separate resources. These resources might go from a node, bare metal, sometimes a VM, could even be a batch slot that has only a few cores inside one node. So we never use multi-machine when we run on HPC resources. What we do actually a submission multi-node, but then one gliding, so a pilot job that prepares the node and runs the actual scientific work, it's running on each node. And all these calculations are independent, so we never use InfiniBand or other interconnect that are connecting and making the HPC machine special. We do use, though, GPUs or resources. Sometimes we even use MPI, but it's reduced on running within a single node with all in memory with all the cores. So the Gleidine is the main component of the system and is doing the node testing and customization. So it's sent to a node, it scouts for resources that are available, and like cores, memory, GPUs, the software and the operating system installed, if there are file systems, and it can run tests specific for the experiment. So when I mention VO, virtual organization, this is an experiment or a group that wants to run some scientific job. Then it's able to customize the node, so it's setting up the environment, loading GPU libraries, starting containers. We use Apptainer, Singularity Apptainer, and doing any specific setup for the VO, installing the software from a shared library, connecting to a database. And it's providing, at the end, customized and reliable execute node that joins the virtual cluster. The factory is another component of the system and is the one that knows how to submit the pilot jobs, these glidines, to the different nodes. So has an idea of what each resource has and knows how to go there, has a configuration, so each resource is tested before starting using it, and knows how to contact, to submit, knows which collaboration are authorized to run there, and other attributes that then are verified eventually and modified by the glidine that's running on the node. The configuration a lot of time is auto-generated from information systems or stored in the Git or other similar systems. So the actual submission to resources using a lot of mechanisms that are provided by HC Condor. The resources are very heterogeneous, so we go from a local cluster to grid side with different protocols to connect to OCC. So when a remote cluster doesn't want to create one of these protocols, there is a VM that's acting as a gateway. And commercial clouds, AWS, Google, there is some also some tests on Azure, open source cloud, and HPC sites. when we run on HPC site, a lot of time what we use to plug them into the whole system, we do basically an SSH tunneling to reach and go to the submit node. And from there, we submit the batch job that run the Glidine and join the virtual cluster. And as I mentioned, usually we always run one Glidine per node, and it's not a multi-node scientific computation. The front end, it's the component that monitors the jobs and see how many pilot jobs are needed, and compares the requests with available resources, and knows about the policies and the expected resources at the site. So decides where to provision the Glidine, the pilot jobs, request the factory to submit them. And the mechanism to create a maximum throughput through the system is to maintain an equal pressure to all resources that are available to run the specific computation. So in the provisioning, knows that a certain number of sites can run a job for that experiment. If GPUs are needed, knows that it's expecting GPUs there. And across all the available resources is sending always jobs in the queue so that they are maintaining the number of idle jobs in the queue that it's considered the pressure. It's also managing the credentials to authenticate both to the site and then to allow the job to transfer files securely or access services. So why so we have like about 90% of the scientific computation that run on these sites that are running inside container. Why did we use Singularity initially and then Apptainer? Mainly because it's unprivileged. So we are running on this site as a regular user. So we never have root. We cannot ask people to install things. If needed, some sites, they might install some software. So at the beginning, we had sites that were installing locally, Singularity, but most of them, they don't. So we have to bring our things and run it as a regular application. Then it has a low overhead. That's important for the application that we run. It's very convenient to have the image being a single file or even the expanded images. I'll talk more about that later. And then we use sometimes the nesting of containers that came useful as well. And we started using Singularity in 2017 in production, so we had tests before. So we went through different evolutions, and we like the direction of being more and more unprivileged and with less requirement on the system. So how it's actually the Glidine, our pilot job, is using Apptainer. So first there is a negotiation that it's actually done and aware, the front end is aware of it. So a site could say, I want all jobs to run in container for security, for isolation, right? Or experiments might want that, but there might be even sites or experiments that they don't want. They want to run on an experiment, say, oh, my calculation has to run on bare metal, right? So there are sites, each site and each experiment, they tell if the containers are required, optional, or they don't want to use them ever, right? So we know where an experiment can run also depending on that. And depending on what they decide, we decide to provision the experiment there and run eventually on a container. Find the runtime executables, we find where Apptainer is available. So recently Condor added in its distribution, so when we start the Condor components that are joining the cluster, a lot of time we have Apptainer available there. Otherwise, it's available in the CernVMFS system as a package, or in other, sometimes there is a system install, or it can be even downloaded. And we have a list of places where we look, and the first one is the one that we will use to run the container. We determine the image, so the experiments can specify a dictionary of images where that can be either downloaded or available on some file system. And the constraint of the sites. And then there is a set of scripts, they are shell scripts, that check that everything is okay and support the Apptainer invocation. And these are used for services. So there might be services that you can run in container that are available to all the jobs that run on that node. For the test scripts at the beginning, some tests are run on the node itself, some are run inside container. And for the user jobs, finally, I said about 90% of the jobs run in container. Some things that we take care of is sometimes path translation. So when the job runs inside the container, they might expect files that were downloaded by the Glidine, and they want to be able to find them, right? And the environment management. So Apptainer is taking care of a lot of it, but we are running a lot of different clusters. We encounter difficulties sometimes with environment file setting of things. So we had to custom configure Apptainer to be able to run there. So the CernVMFS system that I mentioned before, it's write once, read everywhere distributed file system based on HTTP. So what's happening, it's provides the duplication in the file system, is multi-tiered. So in the central server, the tier 0, people write the content, and then it's distributed so that the node, the client, can find everything, and to download the components, it's using HTTP, so it can relies heavily actually on HTTP caching. It's very efficient. And what we do, we expand the images, the CIF images on the file system. They are unpacked. This has the advantage that you don't have to download the whole image, just the part that you access. For example, CMS is one of the experiments at CERN, and has a huge distribution CMS software with all its releases, right? And each release is a few gigabytes. The whole thing is huge. And if you run an analysis or something, you only set up one release and you use only one release. So having the image expanded, they can have in their image all the releases so that they might switch eventually within the job or anything, but only the part needed will be downloaded on the node and cached. And the deployment in CMFS is actually automatic and very easy. So we have a mechanism with the help of the OSG collaboration where we start with a Docker file. We actually build a Docker image for whatever we want to distribute. And on GitHub, we have already a workflow that automatically it's building it and pushing it to Docker Hub. And OSG has a set of scripts that periodically check new version of the image. And once you register them in their repository, they will download and expand them on CVMFS. So we just maintain the images on GitHub, and we get the expanded image on CVMFS. And we use this for distribute, for example, the worker nodes that experiments are used at Fermilab. So the Neutrino experiments at Fermilab, they are used to run in the local cluster, GP grid, and sometimes they used to use also old version of the operating system. There are still experiments that run on Scientific Linux 6. So these, for security reasons, cannot be run or maintained on the site, so they just choose the image that they want to run their software. And a couple of other use cases I want to mention is one where we did a test for Dune, for ProtoDune, to run share GPU. So their workflow, so Dune is LRTPC liquid argon experiment. So they do analysis of tracks that are inside the liquid argon, and their analysis software is using, it's not all Accelerator using GPU, so it's using only part of it is using the GPU. So there was an advantage of sharing the GPU across different jobs that run on the same node. So on Perlmutter, there are many CPU on the nodes, and many jobs can run in parallel within the same Glidine. And what we did, the Glidine is starting first the NVIDIA Triton server, and then all the jobs with the client connect to the same server, and they are able to share that, and they accept a good speed up on the jobs running there. Future work is to share it also across nodes that will include add some latency. We didn't work on that yet. Other uses, it's the benchmarking of nodes. This is especially useful for when we run on the cloud, so that we know which nodes are more performant and cost efficient. And so we have benchmarks expanded on CMFS, and we use to collect information about the node to decide where to run nodes. And here we are running containers inside containers, so the nesting was useful. And another place where we've been running nesting has been in the testing of the GlideinWMS system itself. So at the moment we are testing in Podman containers, mainly because these are kind of more host replicating containers. So we have systemctl even, and we run multiple processes inside the same container. So we prefer to use Podman for that. But inside it, we run the jobs inside containers using Apptainer, and we run also services, and we can do all the testing. And we have basically automated test. The only thing is the credential that a user has to set up, and then is testing new release of the software. And people can do even development with this system, starting with their Visual Studio Code, VS Code, or any other IDE. And thanks to the nested containers, was easier to run in a similar way to what's happening actually in the deployment. So to summarize, GlideinWMS is a pilot-based resource provisioner using high throughput computing workloads. We use Apptainer to run resource validation and the scientific jobs. Mainly because it's some privilege, has a low overhead, allows nested container, and the single file image, and especially the expanded images, are very convenient. And then I presented a couple of use cases to show special uses of it. Any questions?
Can you just have light on the integration with Apptainer and Glidein, like how they work, like integration, and does it Apptainer within Glidein or vice versa? Can you comment on it?
So we use Apptainer within the Glidein. So we have a set of, it's actually a shell script. It uses a library of functions that we can use or other scripts can use. And this takes care of the setup of the initial environment, looking for the executable, matching the exact image, and starting up Apptainer so that people can use it and run correctly. This is a couple of shell scripts and a wrapper that we use for the test script. So that for the within the Glidein, the experiments can run some test script to validate the node or set up things. And for them, it's transparent whether they run in container or not. So we have a wrapper that allows them.
So within it, multiple images of the Apptainers can also be run, right? Is that scenario?
We have one Apptainer runtime. So there can be multiple install. We choose one to run, right, the Apptainer executable. And people can choose multiple images. Yes, they have, for ease of use, they have a dictionary where they have a name and a place where to find it. It could be in the file system or a URL to download it.
Time's up, so thank you, Marco.
Thank you.
Thanks, everybody.